Hi everyone, welcome to our third video in Module 3 of Canese 7103. In our previous videos, we've been talking about distributions of errors and some of the properties of the normal distribution. But right now we want to talk about some of the other assumptions that we're making about errors when we're calculating the proportional reduction of error, and importantly when we want to start to make inferences about the proportional reduction in error. So in our preceding discussions of errors and distributions, we've made a number of implicit assumptions. Right now, we want to make those assumptions explicit so that we know precisely what those assumptions are, and we understand the situations in which those assumptions might be violated. And the reason for this is that this is going to determine the type of statistical test that we're going to want to run, depending on how our data are structured. So we're going to talk about issues, for instance, of dependence and independence, right? And then this is going to influence choices in our this is going to be affected by our experimental design. So for instance, if things are manipulated between people or if things are manipulated within a person, right, that's going to change whether our errors are independent or dependent. And as those assumptions change, the analysis that we have to run changes as well. So the first assumption that we make about errors is independence. And this is the idea that any given error term is not systematically related to another error term. So a good example of this that we use a lot is if we're trying to talk about the heights of people in the room. In an unconditional model, we might estimate the average height for everyone in the room. I'm slightly above average in height, but does my deviation, does my residual tell us anything about the next person's residual, right? And probably not, because there's no fundamental order, no fundamental relationship to how we sort of structure people in the room, right? So my error is unrelated to the next person's error. They might also be above average. They might be below average. And again, that's the room's average, I should say, not just the average height of people. But I might have a positive deviation. Someone else might have a negative deviation. But the fact that knowing something about mine doesn't help you predict with any greater accuracy the next error that you're going to see. So this assumption is violated if knowing one error term allows us to make a reasonable guess, by which we mean it's going to predict better than chance to some degree another error term. So an example of this would be, for instance, time series data. If we're collecting information from one person over different points in time. So we have time nested within a person. So for instance, a player's performance in 2017 is probably more predictive of their performance in 2018 than their 2009 performance. And indeed, this is a correlational structure that you see in lots of time series data. This is what we would call autoregressive. So the nearest time point is closely related to its neighboring time points, but time points that are farther away are less related. Another example would be clustered data. So for instance, if we're dealing with children nested within families, or maybe we have patients nested within different treatment centers, right? We're going to have clusters of data. And certain families are likely to do some things a certain way, whereas other families will do things differently. Or one hospital might administer a treatment one way, whereas another hospital might administer it slightly differently, right? There are things unique to being in that family or being in that hospital. There are things unique to being in that cluster, right, that are going to make observations from that cluster more similar than observations from other clusters. So these are both examples of nested data, and they're both going to create a statistical dependence. Knowing something about one error term is probably going to give us information about another error term. Right? And in the time series case, there's a natural order to the data because we can line things up in a temporal sequence. Whereas with children in a family, for instance, there's not necessarily a natural order to that, right? Which one do I label as child one or child two? Right? I could label them youngest to oldest or oldest to youngest. It doesn't really matter. But there's still going to be a statistical dependence because if one child is above sort of the population level average on a value, there's a real possibility that another child from that same family is above average as well because they're from the same cluster. Therefore, those children are more likely to be similar than they are similar to children from other clusters. So in both of these cases, we have to take that statistical dependence into account. And this independence assumption is very important because unlike the assumption of normality, which we've talked about before, the assumption of independence is very fragile, right? Often people will talk about the assumption of normality as being relatively robust. And that is to say, as long as the underlying distribution is approximately normal, we're going to get a very similar answer, for instance, when we calculate a probability, as if we had a truly normal distribution. However, the independence assumption is not at all robust. So if we fail to recognize and control for statistical dependence in our data, we're going to get a very different, i.e. a very wrong answer. As such, we need to properly identify statistical dependence, and then we need to run appropriate analyses that account for that. Early on in the course, we're going to be talking about situations in which all of our data are independent, right? But as your studies continue, right, we're going to, in this course, talk about a number of situations in which we have statistically dependent data, for instance, repeated observations from the same person. But you, in your statistical studies, might have situations where the analysis is more complicated, right? So you might have multiple levels of clustering. You might have patients within therapists within hospitals, right? Or you might have children within schools within school districts. And these are all our children within classrooms within school districts, right? And these are all different levels of clustering that you might have to account for. So we're going to address statistical dependence in later chapters, and as you develop more statistical tools throughout your studies, it's probably something that you're going to get more and more used to depending on the specific type of data that you work with. So the independence assumption, though, is again very important, and it's a major factor that we have to pay attention to, because if we violate the independence assumption, we're going to get the wrong answer. Secondly, we also make an assumption that our data are identically distributed. Or sorry, not our data, our errors are identically distributed. That is, we assume that all errors are sampled from the same distribution. So for instance, if we randomly sample two groups from the population, right? So I take a sample of people and then I go back to the same population, let's say college students at my university, I sample them again. We would assume that these groups are going to have similar, or what we might call homogeneous variances. So if I'm measuring people on their heights, the distribution of heights, the spread of the heights, should be roughly the same in the two different groups. Now, if I subject people to different treatments, right? So for instance, I sample from the population, I randomly assign some people to the placebo group, I randomly assign some people to a caffeine supplement, we might expect their average level of performance to change when I give them a caffeine supplement. Let's say a caffeine makes you slightly better. However, the caffeine might also alter the variability in your performance. For instance, if it's a perceptual motor task, maybe it makes you a little bit more jittery. So on average, you're aroused, so maybe you do a bit better, but your performance is more variable. So this might create a difference in the variation, or a difference in the variability of the errors between the two groups. So in that situation, I might actually see heterogeneity, or a difference in the variance between my two groups. And that's something that we'll often have to control for as well. And there are different corrections that you can implement in your statistical tests if you see different variances between your different conditions. But if the independence and identical distribution assumptions are met, then this is something that we'll often refer to as IID, or independent and identically distributed. And in most situations, when you sort of see a statistical test presented, it is assuming IID data. And then you either have to choose a different statistical test when that assumption is violated, you have to transform the data, or you have to apply some sort of correction. So if those things are violated, there are different things you can do. You know, all hope is not lost. But in general, sort of our first line of assumptions is that errors are going to be independent and identically distributed. And finally, we make an assumption that our errors are unbiased. And so this means that the mean of all of our errors is 0. This assumption is important because if the distribution of errors, right, averaged either above or below 0, right, let's say the sum of my deviations wound up being negative, or the sum of my deviations wound up being positive, then some systematic error is actually being forced into our model. And so that can cause a problem. Now, depending on the domain in which you work, ensuring that your errors are random and are going to sub to 0 involves different aspects of the experimental design, the measurement tool, and addressing missingness. Okay, so when we have missing observations in our data, there are different things that we can do to control for that. Sometimes you have to remove a subject, sometimes you might impute the missing data, or sometimes the method of analysis might be flexible enough to accommodate missing data. But we're generally going to assume that data in our models are missing at random. Now, in practice, this is not always the case, and data might not be missing at random. So this is a complicated issue that you often have to explore more as you get farther into your particular domain. But for instance, in longitudinal data, data are often more likely to be missing from the end of the study as people drop out or move or just simply get tired of coming. And therefore, we're going to miss more data from the end of the study than we are from the beginning. And this can actually have an influence on our errors, and it can have an influence on our model, and it might be introducing some systematic bias into our model if we don't account for it appropriately. So again, these are some of the implicit assumptions that we made in the previous chapter, or in the previous discussions. But now we're trying to make these explicit so that you're aware of them and that you consider the influence that independence, identical distributions, and unbiasedness have when you're trying to think about how your data are structured and what the appropriate statistical analysis is in the future.